Hello everyone, so today I'll be going over Codeforces round 810, and this was a kind of controversial contest because for Division 2, Problem E, it was a repeat of like an ICPC contest. I think it was like either 2015 or 2016, and then also for Division 1, Question C, it was the same thing, so they made Division 1 of the contest unrated, but Division 2 stayed the same, which is pretty good because I actually did gain 52 rating. So yeah, let's go over the problems. So in the first problem, basically you're given an integer n, and then based on that integer, like you're given like the permutation, or you're not given the permutation, but you assume the permutation because the permutation of every integer n will always be the same. And a permutation is if n is equal to, let's say, 5, like an arbitrary number, a permutation would be the use of every number from 1 to n inclusive. So this is a permutation of n, this is a permutation of n, and yeah, it's just any combination of that, it's a permutation, but you can't have any repeating numbers like this because there's two ones. Let me draw a better 3. Not like that's better, but yeah. So you can't do that or anything like that. You can't leave out numbers, so you can't have like no ones and then like just a 2, 3, 4, 5. It has to include every number from 1 to n inclusive. So yeah, basically you're given n, and then so the permutation of that would be 1. For 4, it would be 1, 2, 3, 4 because that's 1 to n. And you want to find out the minimum weight that you can have from that permutation, like create a permutation with a minimum weight. And to create a weight, you have to have p sub I over I. So this would be 1 because p sub I divides I. So I in this case is going to be 1 because, okay, let me draw it out to make it easier to understand. So the permutation of that number, of the answer, is 2, 1, 4, 3. And this is the answer because it's the least amount of weight. And we can calculate this because the index of these are 1, 2, 3, 4. We know this because this is the first element, this is the second element, this is the third, and so forth. And we get the weight by putting this number over this. So I should probably put this under, like put these under one another. Let me delete this. Or move it over here. And so we just put this over this, 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 this. And basically, if it divides it, like if this divided by this is a whole number, then it will be at a weight of 1. So this would, since this divided by this is even, then you add 1 to this. Since this is 1/2 and is not a whole number, it's 0. Sorry, that was ugly. Let me actually put it on top. So there's 1, 0. This is 0 because it's not a completely whole number. This is 4 over thirds, and you need 3 over 3 in order to make it a whole number or something. 3 over 3, 6 over 3, 9 over 3, any multiple of 3's. And this is not a whole number either because it's a fraction. And so the total weight would be 1. And we can see a pattern here. We notice that as long as only the first number is weighted, then it'll be the minimum weight, because we know that only the first one like has to be weighted because any number over 1 is bound to be weighted. And so we can create a pattern, like a certain pattern for each test case that's always going to be set. Basically what we do is we put the highest number on it. So let's say 4, because in this case 4 is the highest given permutation, because when n is equal to 4, then that's the highest number because it's from 1 to n, so n has to be the highest. We put n as the first number, and then we shift everything else. So the permutation is going to be n, and then 1, and then 2, and then 3, so forth. But in this case, n is going to be 4, so it's going to be 4, 1, 2, 3, which is still a permutation, so it counts. We put this over the index. And so n over 1 is always going to be weighted, so this will always be weighted. And so the answer will always be 1. The minimum weight will always be 1, no matter what. Because then we can imagine this as like 2 runners, and we have a runner going at like, I don't want to include like something, a hard concept, but if it helps, you can imagine like this. Like there's 2 runners, but one runner gets a head start of 1 meter, and they run the same speed. And so this runner, the runner in the back, will never catch the runner in the front, because the runner in the front always has the same speed, and it's always matching the runner on the back, but the runner in front will always be 1 meter ahead. And so we can think about it like this: the bottom is always 1 meter ahead, and so the top over the bottom will never equal 1, because it's always one fraction off. And yeah, so the code is extremely simple once you understand the pattern. Basically, you input the test cases, and for each permutation n, you want to first print out n, which is the largest number, and then after that print out from 1 to n minus 1. So that's exactly what we did. We first printed out n, and then we print it from 1 to n minus 1, which is this little area. So 1 to n minus 1, n is 4, so n minus 1 would be 3. So moving on to question B. This one I had trouble with and only was able to solve it after the contest, but it seems like a bunch of other people had trouble with it because it was pretty hard. So basically, you're given a party. So you have a party, and you have like a certain number of people, n people, and you're also given m different friend groups or friend pairs. So friends can come into the party as pairs, and if they come in as a pair, then it's tradition to eat cake together, and they share one cake. And so the baker, though, creates cakes only in pairs of 2, and so in order to include like friend pairs, you have to get an even amount of friend pairs, or else it won't work. So let's say in the third test case, this one, basically, if you just include the friend pair of 1 and 2, it won't work, because 1 and 2 would only share one cake because they're one friend group. But the baker bakes in 2, so you need another friend group to match it. So let's say add 1 and 4. So now that's even. So now this would work because 1 plus 1 is equal to 2, and the baker does work for these. But the thing is, you want to find the minimum amount of unhappy people. So that's your goal, the minimum amount of unhappy people. And an unhappy person is formed when someone in this like n columns, or n, like the array of n elements, gets left out. So if they can't go to the party, either because it doesn't fulfill the even cake requirement, or for some other reason, like you don't want to allow them, because I think, yeah, that's the only reason, when the cakes aren't even, because otherwise you want to include everyone. So yeah, if the cakes are uneven and you have to leave someone out, then that person will have an unhappiness of a sub I. So if person 3 is unhappy, then he'll have an unhappiness of 3 because that's his index. And I think this is not the best example because they're all linear. So let's say in this case, if person 1 is unhappy, so this is person 1, this is person 2, this is person 3. Let me draw it out. So this is person 1, this is person 2, and this is person 3. If person 1 is unhappy, then the total unhappiness would be 2, because that's a sub I. And we just want to minimize the amount of total unhappiness. And we see that to combat like half the test cases, if m is even, we know that for sure the total amount of unhappiness would be 0, because everyone will be left happy because there's an even amount of cakes, so there's no one who will be unhappy. So let's say, since there's no like really good even m test cases in the sample test case, let's create our own. So let's say m is equal to 4, and there's going to be m rows of pairs. So let's say we have 1 and 3, 2 and 4, 1 and 6. No matter what, let me add 2 and 5 again. Okay, so no matter what, this would always fulfill the requirements because these come into a pair. So that's one cake, this is another cake, this is a third cake, and this is a fourth cake. And the baker bakes in 2, so he can just bake twice. And so if m is even, then the requirements are always fulfilled and you don't have to worry about it. There's going to be no one unhappy because everyone can come to the party. But if m is odd, I can just keep this and add on to it. Let me delete this and add it to 5. So if m is odd though, then you have 2 choices. So you want to subtract the least amount of people from the party in order to make it as many people happy. So what you can do is you can either find someone with a degree of odd numbers. So essentially what a degree is, like if you view this as a graph, you want to see someone who's connected to an odd amount of people. So let's say in this case 4 is connected to only 2, and so that's a degree of 1. And so if we remove 4, then it just removes only one pair. Let's add an extra one since m is equal to 5. 4 and 6. Oh shoot, I can't use 4 because that's going to be counterintuitive. 2 and 6. So yeah, over here we have to remove an element with a degree of an odd degree. And so what we do is we take away if it's odd, but we want to do like the minimum of that, because then we want to minimize like the amount of people who aren't in the party. And if that's not enough, if somehow like the single elements are larger than the double, then we check the pairs. So let's say we have 1 and 3. Let me draw it out here, or I can just do this. This is not working. Okay, there we go. So I do believe it's 2 and 4. So what we can do is we check like the total amount. So by removing exactly one pair, it'll make the amount of pairs going to the party even, which will fulfill the requirement. So I hope you see now that all like the code is trying to do, all we're trying to do is remove, if it's odd, is to remove one pair from the party in order to make this even, to make the amount of people going here even. And so we just check this plus this, which is 4, this plus this plus this, and so forth. And we want to minimize like the sums. We want to find the minimum of that, and whichever is the minimum, we cross it out. So in this case, this would equal to 6, 7, another 7, and 8. Oh, it's ugly. So the minimum in this case would be this one. And so we remove this, and so the most amount of people can go to the party, or we minimize the unhappiness, because these people have an unhappiness of 4 combined, and so if we remove them, then the total unhappiness would just be 4, which is a minimum out of all of this, which fulfills the requirements. And so let's look at the code. Basically what I do is I just input the things, create a pair array, and also a counting array, and to count the degrees. And I start inputting the x and y, and in order to make it 0 indexed, because over here it's already 1 indexed, I subtract 1 from x and y, because as you can see over here, person 1 and person 2 means this person and this person, but in an array in C++, it's in 0 indexing, meaning that they count this as 1, they count this as 1. I'm sorry, they count this as 0, this is 1, this is 2, and so forth. And so to make it consistent, I have to subtract 1 from both x and y. After that, I add the pair to the edges, to the array edges. And over here you see like the edge case where m is even, then you know that for sure everyone can go to the party, because the only reason why like a pair of people or someone can't go to the party is because the amount of cakes is odd. So yeah, if it's odd, then this is 1 cake. They share 1 cake, remember? Like pairs share 1 cake. And the baker can only bake in 2s. And so this works. It's a check mark. But since if you add 1 more, the baker doesn't bake in 3s, or they don't bake individually. So you have to leave this person out. And so that's that test case. And I set answer to the maximum because I want to find the minimum. If I set it to anything too low, you'll get the wrong answer. So I have to set it to the highest maximum integer. And then for each element in the degree counter, I check if that's the minimum. So I check that like degree counter, and if that degree counter is odd, so if that element has a odd degree, then I like make the answer like the minimum of that and also that number. Essentially, it's let me draw it out for you again. Sorry, I don't know what's going on. Okay. So we have 1 and 3. Basically what it does is it checks the degree of each element, and what a degree is how many people are connected to it. So let's say the degree of 1, like this element 1, is equal to 2 because it's connected to 3 and it's connected to 6. The degree of 2 would equal to 3 because it's connected to 4, 5, and 6. You get the point. So if the degree of a number is odd, then you want to take it away, because that means it's connected to an odd amount of people. And assuming that it's already odd because you got rid of the test case where m is even, so if it's odd, then you want to remove an odd amount of people from the party, which therefore makes it even. Because if you have, so any even number, like where m is equal to 4 or m is equal to 2, it's already combated over here. It continues, so this doesn't matter. So when m is even, it doesn't matter. It's just 0. But if m is odd, like let's say 3 or 1 or 5, if you remove another odd number from this, so let's say we remove 1 from 3, which equals to 2, because 3 minus 1 is equal to 2. 2 is even, so now it works. So anytime you have an odd number, if you subtract an odd number, hence subtracting odd degrees, then the amount of pairs of people will now be even. So that's all we're trying to do. We're just trying to find the amount of oddly connected people, like, which is also degrees, known as degrees. So if it has an odd degree, such as 4, it's only connected to 2. If we remove 4, 2 is still here, but 4 is gone. So that pair is removed. And so, yeah, that's basically what it does. And it keeps a track of like the minimum amount. So that's what this part does. Because we want to remove the minimum amount of unhappy people, and that works by just subtracting a sub I. Or, yeah, like removing a sub I from it. And assuming that's not enough, we look at over here, and it basically just checks if the edges, like this plus this edge, is the minimum as well. So all it's doing is adding this and then this and so forth, and then checking which one's the lowest, assuming that that is lower than this. And yeah, that's all there is. Thank you for watching. If I helped at all, you can please do like and subscribe. If you have any questions whatsoever, feel free to comment. And yeah, thank you for watching.